The universe is mostly made of stuff we cannot see. In that profound darkness, cosmic monsters might be hiding. I am talking about dark stars, theoretical giants from the dawn of time, powered not by nuclear fire, but by the annihilation of dark matter itself. By the end of this journey, you will have explored 25 undiscovered dark stars that could rewrite the story of our cosmos. What if the first light did not come from stars as we know them? What if the center of a galaxy is not a black hole but something even stranger? Are you ready to question everything you thought you knew about the night sky? Our story begins not with a bang, but with a slow, cold gathering in the absolute dark. In the aftermath of the Big Bang, the universe was a formless, expanding sea of hydrogen and helium gas, utterly dark and silent. But within that primordial fog, the first seeds of structure were quietly taking root. Gravity, the universe's great architect, began to pull the densest patches of gas together. In one of these patches, something extraordinary happened. It did not collapse into a normal star. Instead, it grew and kept on growing, feeding on the invisible scaffolding of the cosmos. This is the first of our undiscovered giants, dark star number 1, the primordial seed. Think of it not as a star in any familiar sense, but as a cosmic furnace of a completely different kind. Its raw material was the pristine gas of the young universe, but its true engine was something we cannot see. As this immense ball of hydrogen and helium, hundreds of times more massive than any star cluster we know, began to form, its incredible gravity did more than just pull in gas. It also began to trap the dark matter that was swirling through the early cosmos. These mysterious particles, drawn into the star's heart, would collide and annihilate each other, releasing a steady torrent of energy. This energy was the star's lifeblood. It created an outward pressure so powerful that it halted the normal process of stellar birth. The core never became hot and dense enough to ignite nuclear fusion. The fire that lights our sun never sparked. So what powered this behemoth? Pure annihilation. The slow, constant destruction of dark matter provided all the heat and light this object would ever need. It would have glowed with a soft, diffuse light, not the fierce, blistering glare of a young sun, and its scale is almost impossible to comprehend. Theoretical models suggest a primordial seed could have ballooned to millions of times the mass of our own sun. To put that in perspective, if you place this dark star at the center of our solar system, its surface would extend far beyond the orbit of Pluto, swallowing every planet whole. It would be a gentle, warm, and terrifyingly vast presence, but its true legacy was not its light, it was its gravity. An object of such staggering mass would have acted as a gravitational anchor for the entire region around it. It would have pulled in vast streams of gas, sculpting the early universe and seeding the formation of the first galaxies. The galaxies we see today, including our own Milky Way, might have grown around the ancient, faded corpses of these primordial dark stars. They were the silent, invisible foundations upon which the visible universe was built. So the next time you look up at a galaxy, you might not just be seeing stars. You might be looking at the ghostly footprint of a primordial seed, a relic from a time when the rules of creation were written in darkness, but a dark star that vast could not remain alone in the void. Its immense gravity would have pulled the cosmos toward it, creating the first structures in the universe. Yet some of these giants may have chosen a different path, one of profound isolation. This brings us to our second undiscovered dark star, the phantom in the void. Picture the largest structures in the universe, the great cosmic web. Galaxies cluster along shimmering filaments of gas and dark matter, like glittering cities connected by luminous highways. But between these brilliant threads lie the voids, unimaginably vast deserts of near-nothingness. These regions are not completely empty, but they are so sparse that a single galaxy would stand out like a lone lighthouse in an endless, dark ocean. It is here, in one of these cosmic deserts, that a phantom might reside. This dark star would be a solitary leviathan, a million solar masses of hydrogen and helium, powered silently by dark matter annihilation. But with no nearby stars to illuminate and no dense gas clouds to sculpt, it would emit almost no visible light. It would be a ghost, a shadow against the deeper black. So how could we ever hope to find something that gives off no light, in a place where there is almost nothing to see? Astronomers would have to look for the imprint of its gravity, the only signature such a phantom could leave. One method involves studying the dark matter halos of the few, faint galaxies that might skirt the edges of the void. The gravity of a hidden dark star would warp and tug at these halos, creating a distinct pattern in their motion that cannot be explained by the visible matter alone. It would be like watching a handful of leaves floating on a calm pond suddenly swirl in an invisible eddy, revealing a submerged current. An even more subtle technique relies on a cosmic quirk of gravity, gravitational lensing. The immense mass of the phantom would warp the very fabric of space-time around it. If a distant, background galaxy happened to lie directly behind this dark star from our point of view, its light would be bent and distorted as it passed through this warped space. The galaxy's image might be stretched into a faint, smeared arc, or split into multiple, identical mirages. Finding such a lensed image in the middle of a void, with no visible object to cause the lensing, would be the ultimate clue. It would be the signature of a massive, invisible presence. The challenge is staggering. These signals are incredibly faint, buried in noise and competing gravitational effects. Confirming a phantom would require painstaking observations from the most powerful telescopes, combined with complex computer models to rule out every other possibility. It is a search for a whisper in a silent room the size of the universe. Yet if found, a phantom in the void would tell us something profound. It would mean that the first dark stars were not just the seeds of galaxies, but also cosmic hermits, choosing a life of solitary darkness. And it would force us to ask, what else is hiding in the empty spaces where we have never thought to look? The center of a galaxy is supposed to be a place of ultimate darkness, a supermassive black hole with an event horizon from which nothing returns. But what if, in some quiet corner of the cosmos, that central monster is not a black hole at all? Our third undiscovered dark star is the Galactic Core Pretender, a dark star of staggering mass sitting on the throne of a dwarf galaxy, masquerading as the king. Dwarf galaxies are the small, faint building blocks of the universe, often orbiting larger galaxies like our Milky Way. At the heart of many, we expect to find a proportional black hole, perhaps a few 100,000 times the mass of our Sun. A galactic core pretender would match that gravitational weight, but its nature would be fundamentally different. Its immense gravity would whip stars into the same frantic orbits, creating the same telltale swirl of motion we use to detect black holes. From a distance, the gravitational signature would be nearly identical, but there is no point of no return, no event horizon. The dark star would have a true surface, a physical boundary of superheated gas. This distinction creates a potential clue in the form of light. A supermassive black hole, when it is not actively feeding, is famously dark and quiet. A dark star of similar mass, however, would be constantly powered by the annihilation of dark matter particles at its core. This process would generate a steady, low-level glow across multiple wavelengths, a soft hum of energy that a dormant black hole simply would not produce. It might emit a faint, unusual spectrum of light, or a subtle excess of high-energy radiation like X-rays, coming not from a hot accretion disk but from the star's own fiery heart. Astronomers are now conducting deep surveys of dwarf galaxy cores, mapping the motion of stars with incredible precision and studying their faint emissions. They are looking for an anomaly, a core that has the gravity of a monster but the gentle, persistent light of something else entirely. Finding a galactic core pretender would be a cosmic revelation. It would mean that the dark stars of the early universe did not all vanish. Some may have survived, sinking to the centers of the first small galaxies and growing even more massive over billions of years. They would be living fossils, hidden in plain sight, challenging our most basic assumptions about what lies at the center of a galaxy. The true ruler of that distant dwarf system might not be a hole in space, but a star born from the dark. But a galactic core is not the only place a dark star could hide its true nature. Sometimes, the most revealing clues come from a cosmic dance partner. Our fourth undiscovered dark star is the dark binary partner, a silent giant locked in a gravitational waltz with a normal, sun-like star. This pairing would create a celestial detective story written in light, gravity, and subtle, telling anomalies. Imagine a star like our own, tracing a graceful ellipse through space. Yet its motion is not perfectly smooth. It tugs and wobbles along its path, as if pulled by an invisible hand. This is the classic signature of an unseen companion, a method we have used for centuries to find planets and dim stellar corpses. But in this case, the companion's gravitational pull would be far too strong for a planet, and yet it emits no visible starlight of its own. That alone would make astronomers deeply suspicious. The orbit itself could hold the first major clue. A dark star powered by annihilation would not have the same internal structure as a fusion-powered star of equal mass. Its core might be less dense, or its energy production might be spread throughout its volume differently. This subtle difference in its gravitational field could imprint a unique fingerprint on the binary orbit, a tiny deviation from the perfect ellipse predicted for two normal stars. Detecting that would require exquisitely precise measurements of the visible star's position over many years, but it is within the reach of our most advanced observatories. Yet gravity is not the only way the dark partner would betray its presence. Its power source is a constant, internal glow of annihilation radiation. While the dark star itself might not shine brightly in visible light, this radiation, especially high-energy X-rays or gamma rays, would flood the space around it. If the normal star orbits close enough, one side of it would be perpetually bathed in this eerie, invisible light. This could heat that hemisphere of the star more than the other, creating a strange and persistent temperature imbalance. From our vantage point as the stars orbit, we would see the normal star's brightness and color change in a regular, repeating cycle, not because of eclipses, but because we are seeing its hotter, irradiated face, and then its cooler, unheated face. It would be like watching a lighthouse beam sweep across a landscape, except the light is invisible, and we only see the warmed ground begin to glow. Finding such a system would be the closest thing to a smoking gun. It provides multiple, cross-checking lines of evidence: the gravitational wobble, the anomalous orbital details, and the telltale asymmetric heating of the visible star. It is a complete package of clues that together point overwhelmingly to one conclusion: a star powered by dark matter. This dark binary would be more than a curiosity. It would be a pristine laboratory. By studying the dance between the visible and invisible star, we could measure the dark star's mass and size with incredible accuracy. We could sample, indirectly, the radiation from its core, learning about the properties of the annihilating dark matter particles themselves. It would transform a theoretical phantom into a measured, physical object, giving us our first direct window into the engine that may have started it all. So the key to finding a dark star might not be staring into the abyss, but carefully watching a star that is not dancing alone. There is a silent chapter in the cosmic storybook, a time after the primordial glow faded and before the first true stars sparked. This era is called the Cosmic Dark Ages, a period of profound blackness lasting hundreds of millions of years. It is here, in that deep and formative quiet, that our fifth dark star was born. The relic from a dark age is not just old. It is a living piece of the universe's lost childhood, a fossil that never stopped shining in its own strange way. While the rest of the cosmos was utterly dark, This object formed from a rare, dense knot of hydrogen and dark matter. Its dark matter engine ignited, and it began to glow with that soft, annihilation-powered light, a lonely beacon in an otherwise lightless universe. For eons, it was possibly one of the only sources of photons in its entire region of space. Its gentle ultraviolet radiation would have slowly cooked the hydrogen gas around it, stripping electrons from atoms in a process called ionization. This means a Dark Age relic would have created a small, early bubble of ionized gas, a bright fingerprint in the darkness long before the first supernova ever exploded. The true wonder, however, is that it might still be here today. To survive for over 13 billion years, a dark star needs a stable environment and a continued fuel supply. This relic likely found sanctuary in the halo of a modern galaxy like our Milky Way. Galactic halos are vast, sparse spheres of old stars, dark matter, and lonely gas clouds that surround a galaxy's bright disk. Here, far from the violent collisions and intense radiation of the galactic core, a dark star could persist in a state of near-perfect preservation. It would drift slowly through this quiet frontier, still feeding on the halo's diffused dark matter, its internal fire burning low and steady. Spotting such a relic would be a monumental challenge. It would be incredibly faint, lost among the countless ancient normal stars in the halo. Astronomers would search for it by looking for an object with a highly unusual chemical signature. A true relic from the Dark Ages would be composed of absolutely pristine material hydrogen and helium and nothing else. It would contain none of the heavier elements like carbon, oxygen, or iron that are forged inside normal stars and scattered by their explosions. Finding any star in our galaxy's halo with zero metals, as astronomers call these heavier elements, would be a sensation. Finding one that also emits an unexplained, soft glow of excess radiation would point directly to a dark star origin. The implications of discovering a Dark Age relic are staggering. It would be a direct probe into a time period we can never observe directly. By studying its light and its environment, we could learn exactly how the first structures gathered in the darkness. More profoundly, it could rewrite the timeline of cosmic reionization, the epoch when light finally broke the universal darkness. If many such dark stars existed, their combined, gentle glow could have begun the process of reionizing the universe millions of years earlier than we think, slowly preparing the cosmos for the brilliant dawn of normal stars. This relic would not be a silent fossil. It would be a whisper from the universe's first morning, carrying a story we have only ever guessed at. Some dark stars may have been born in the chaos of a galactic nursery, only to be cast out into the endless night. Our sixth undiscovered giant is the Rogue Wanderer, a dark star exiled into the intergalactic void. Its story begins not with quiet formation, but with cosmic violence. Picture two small, primordial galaxies, each perhaps cradling a dark star at its heart. Over billions of years, their mutual gravity pulls them into a slow, inevitable dance that ends in a cataclysmic merger. As the galaxies smash together, their stars are flung in chaotic new orbits by immense tidal forces. In this gravitational maelstrom, the dark star at the center of one galaxy could receive a tremendous slingshot kick. It is ejected from the merging system entirely, hurled out into the empty space between galaxies at speeds of hundreds of kilometers per second. In an instant, it becomes a true cosmic castaway, leaving behind the faint glow of its birthplace to embark on an eternal, solitary journey. Now it drifts through a profound and empty ocean. The space between galaxies is the closest thing our universe has to a true vacuum. Here, the Rogue Wanderer encounters almost nothing. No dense gas clouds to light up, no star clusters to distort, no planetary systems to warm. Its dark matter engine continues to burn, providing a faint, internal glow. But with no material to illuminate, it is virtually invisible. This perfect isolation is what makes finding one perhaps the most daunting challenge in our entire search. Without any nearby luminous objects to interact with, it leaves no traditional astronomical signature. We cannot look for a wobbling star or a lensed galaxy because there are none around it. So how do you find a needle in a universe-sized haystack when the needle gives off no light? The answer lies in the most delicate measurement of gravity itself. As the rogue wanderer travels, its immense mass subtly warps the fabric of space-time around it. This warping creates a moving gravitational lens. If by incredible chance, the path of this dark star aligns perfectly between our telescopes and a distant, background galaxy, a brief and extraordinary event could occur. For a short time, days, weeks, perhaps months, the light from that faraway galaxy would be bent and magnified as it passes through the warped space around the wanderer. From our point of view, the background galaxy would suddenly, and for no apparent reason, brighten and then fade again as the dark star moves through our line of sight. Astronomers call this phenomenon a microlensing event. We use it to find planets and faint stars within our own galaxy. But detecting a microlensing event caused by an object in intergalactic space would be a signal of a completely different order. It would require monitoring millions of distant galaxies continuously, searching for those unexplained, transient flashes of magnification with no visible cause. The data would be a whisper of gravity from an unseen, moving mountain of mass. Finding a rogue wanderer would tell a story of cosmic ejection we rarely consider. We often think of galaxies as stable islands, but their histories are written in collisions and expulsions. This dark star would be a living testament to a violent merger that happened billions of years ago, a piece of galactic shrapnel frozen in time. Its very existence would prove that the seeds of the early universe could be violently scattered, and that some may still be out there, traveling the infinite roads between the islands of light. It forces us to wonder what else might be moving in that darkness, unseen and untethered, carrying the secrets of a forgotten home. The deepest shadows in space often hide the most intriguing secrets. Within the vast, cold clouds known as dark nebulae, where dust and gas blot out the light of stars behind them, another kind of darkness might be brewing. This is dark star number 7, the dark nebula's heart, a stellar phantom born in the perfect cosmic hiding place. Imagine one of these nebulae not just as a simple veil of dust, but as an exceptionally dense knot of cold dark matter, a gravitational well so deep it begins to pull in the surrounding hydrogen gas. As the gas accumulates, it traps even more dark matter at its core. Here, shielded from the prying eyes of optical telescopes by the nebula's own opaque cloak, the dark matter particles begin to annihilate. A dark star ignites, but its faint, soft glow of annihilation radiation is immediately swallowed by the very cloud that gave it birth. To an outside observer, this region would appear as nothing more than a slightly deeper patch of blackness within an already dark nebula, a knot of shadow within a shadow. It is the ultimate camouflage. So how could we ever hope to see a star that is actively hiding? We must look for the energy it cannot completely conceal. While the visible light from its core is absorbed, the higher energy radiation it produces might just leak out. The surrounding nebula, thick with dust, would absorb the star's lower energy photons and re-radiate that energy as heat, glowing faintly in the infrared part of the spectrum. Astronomers could scan the hearts of the largest, coldest dark nebulae, searching for a mysterious point source of infrared warmth, with no corresponding visible star to explain it. It would be like feeling a pulse of heat from within a bank of fog, with no fire in sight. An even more tantalizing clue would be a pinpoint of gamma rays. This extremely high-energy radiation, a direct product of dark matter annihilation, can punch through dust and gas that blocks ordinary light. A faint, steady gamma-ray signal emanating from the core of a dark nebula would be a stunning anomaly, a scream from the silence. Finding the dark nebula's heart would force us to rethink these cosmic clouds. We see them as passive curtains, but they could be active cradles, nurturing monsters we never thought to look for. It suggests that dark stars are not just relics of the distant past. They could be forming quietly, even now, in the coldest, darkest corners of our own galaxy, hidden in plain sight until we learn to see the heat they leave behind. The most brilliant beacons in the universe are quasars, the cores of distant galaxies where supermassive black holes feast. Their light can outshine 1 trillion suns. But what if one of those dazzling points is not a black hole at all? Our eighth dark star is the quasar Mimic, a theoretical object of almost unimaginable scale. It begins as a primordial seed of staggering proportions, perhaps hundreds of millions of times the mass of our Sun. Its dark matter engine would not be a gentle flicker, but a continuous, titanic explosion of annihilation at its core. The energy released could rival the output of a small quasar, flooding its surroundings with a fierce, luminous glow that would be visible across the cosmos. To a distant astronomer, it would appear as a brilliant, star-like point, a quasar in every apparent sense. The deception, however, lies in the details of its light. A true quasar's brilliance comes from a superheated accretion disk, a whirlpool of doomed gas spiraling into a black hole at nearly the speed of light. This frantic, violent environment produces a very specific signature in the quasar's spectrum, a pattern of light split into broad, smeared emission lines caused by gas moving at tremendous velocities. The quasar Mimic would lack this crucial fingerprint. Without a black hole and its frantic disk, there would be no such extreme motions. Its spectrum would be smoother, perhaps showing only the subtle features of the hot gas at its own surface, or the glow of the surrounding material it has heated. Its light might also be remarkably steady. While quasars often flicker and flare as their accretion rate changes, the dark star's power source, the steady annihilation of dark matter, could provide a far more constant and unwavering luminosity, a clockwork beacon in the chaotic dark. This presents a fascinating challenge for the next generation of observatories. Projects like the Vera Rubin Observatory will scan the sky nightly, discovering millions of new quasars by their brilliant point-like appearance and redshift. A quasar Mimic could easily slip into those catalogs, initially classified as just another distant active galaxy. It would take a dedicated, second look with powerful spectrographs to reveal the truth. Astronomers would point the world's largest telescopes at this brilliant dot, expecting to see the broad emission lines of a supermassive black hole. Instead, they would find a spectrum that is strangely calm, lacking the telltale turmoil. It would be the cosmic equivalent of hearing a roar and expecting a lion, only to find a different kind of beast entirely, one that produces the same volume with a completely different mechanism. Discovering a quasar Mimic would force a profound revision of our cosmic census. It would mean that not all brilliant point sources are hungry black holes. Some could be the last, largest survivors of the first generation of dark stars, having grown to truly monstrous proportions, masquerading as the universe's ultimate monsters while being something entirely alien. It suggests that the dawn of light may have been lit by two different kinds of fire, and we may have been crediting only one of them for all the brilliance we see. Far from the brilliant spiral arms of a galaxy, a different kind of frontier exists. In the vast, spherical halo of dark matter and ancient stars that surrounds galaxies like our own, another dark star keeps its watch. This is the Galactic Halo Sentinel, a solitary giant adrift in the galaxy's outermost darkness. It is not a relic from the Dark Ages, but a later formation, born from a dense knot of dark matter in the halo itself. Its position is one of profound isolation, tens of thousands of light-years above or below the bright galactic disk, where the star density is so low that the night sky from a hypothetical planet orbiting it would be almost completely black, save for the faint, misty band of its host galaxy stretching across the heavens. This sentinel is a guardian of the unseen, its immense mass tracing the contours of the galaxy's true dark matter skeleton. Finding such an object seems nearly impossible, yet its very isolation provides unique detection opportunities. One method involves listening for its silent song of annihilation. The dark matter particles annihilating in its core would produce a steady stream of gamma rays, the highest energy form of light. From our vantage point within the Milky Way, a halo sentinel would appear as a faint, unresolved point source of gamma rays, a persistent pinprick of high-energy light against the diffuse gamma-ray background of the galaxy. The challenge is distinguishing it from other gamma-ray sources like distant pulsars or the remnants of ancient supernova. The key signature would be its spectrum, the specific energy fingerprint of the gamma rays, which could match predictions for dark matter annihilation rather than other astrophysical processes. It would be a whisper of pure particle physics echoing from the dark. An even more elegant detection method relies on the Sentinel's gravity and its lonely post. Because it floats in the relatively empty halo, with few stars nearby to complicate the signal, it is a perfect candidate for a specific kind of microlensing event. Astronomers monitor millions of stars in nearby galaxies, like the Magellanic Clouds, watching for the telltale brightening that occurs when a massive object passes directly in front of them. Most microlensing events caused by normal stars or planets last for days or weeks. A dark star with the mass of 1,000 suns, however, would create a lensing event that could persist for years. Its immense gravity would bend and focus the background star's light for a much longer duration, creating a slow, majestic brightening and fading that stands out dramatically in the data. Finding such a long-duration microlensing event with no visible lensing object would be a powerful indicator of a massive, dark body in our galactic halo. Discovering a galactic halo sentinel would do more than just add another entry to our list. It would provide a direct, localized measurement of the dark matter halo's structure. By pinpointing its location and mass, we could map the density of dark matter in that specific region with unprecedented accuracy, turning a theoretical halo into a charted territory. This sentinel would not just be hiding in the darkness, it would be illuminating it, acting as a natural probe into the most dominant yet elusive component of our galaxy. Its silent vigil helps us see the invisible architecture of our cosmic home. Gravity loves company, even in the dark. While we have been hunting solitary giants, the early universe might have forged them in families. Our 10th undiscovered dark star is not one object, but an entire brood, the dark star cluster progenitor. This is a gravitationally bound group of dark stars, born together from a single, exceptionally rich reservoir of primordial gas and dark matter. Think of it as a stellar nursery, but instead of giving birth to hundreds of sparkling suns, it produced dozens of these dark behemoths, each glowing with its own internal annihilation fire. They would orbit one another in a slow, stately dance, bound by their collective gravity into a single, massive, and profoundly dim structure. From a distance, this cluster would present a profound puzzle. It would contain the gravitational heft of a small galaxy, perhaps millions of times the mass of our Sun, all concentrated in a relatively compact region of space. Yet when you point the most powerful optical telescope at it, you would see almost nothing. A handful of faint, wispy stars might be visible, normal stars that formed later or were captured, but they would account for only a tiny fraction of the mass needed to explain the fierce gravitational grip the object clearly possesses. The vast majority of its substance would be completely invisible, a ghostly anchor holding everything together. This exact scenario is what astronomers see in some of the universe's most enigmatic objects, ultra-faint dwarf galaxies. These are tiny, diffuse collections of stars that orbit larger galaxies like our Milky Way. Their few visible stars move at surprisingly high speeds, suggesting they are held in the grip of a much more massive, unseen object. A conventional explanation is a hefty dark matter halo, but a dark star cluster could offer a compelling alternative. Instead of a smooth cloud of dark matter, the core of such a dwarf galaxy could be packed with a family of dark stars, providing the concentrated gravitational punch to explain those frantic stellar orbits. The same mystery applies to certain ancient globular clusters, dense balls of hundreds of thousands of normal stars that orbit galactic halos. A few of these clusters exhibit a curious anomaly, their outer stars moving just a bit too fast for the amount of visible mass we can count. The missing mass is often attributed to dark matter, but its origin in such a tight cluster is a puzzle. A dark star cluster progenitor, perhaps captured by the globular cluster long ago or forming at its heart, could be that hidden anchor. A few dozen dark stars nestled in the cluster's core would provide the extra gravitational glue without emitting the light that would give them away. Finding such a progenitor would require looking for the subtle, combined glow of its members. While each dark star is faint, the collective infrared or soft X-ray emission from dozens of them might create a detectable, extended haze at the heart of an otherwise dim dwarf galaxy or a puzzling globular cluster. It would be a signature of warmth and energy with no visible source, a hearth fire burning in an empty hall. Discovering this dark family would rewrite the story of how the first structures bound themselves together, proving that the universe's initial building blocks were not just individual seeds, but sometimes entire dark orchards, whose strange fruit still hangs in the cosmic tree, invisible and heavy with the weight of the beginning. The universe is not a static place, and even a dark star's steady glow might falter or flare. Our 11th undiscovered giant is the transient Annihilator, a dark star whose power source flickers like a faulty lamp. Its story hinges on its environment. Unlike a solitary wanderer in the void, this dark star orbits through the dense, clumpy dark matter halo of its host galaxy. Its path is not a smooth circle but a journey through hills and valleys of invisible matter. For long periods it drifts through sparse regions, its dark matter fuel supply running low. Its internal fire dims and the star becomes almost undetectable, a cold ember in the dark. Then, its orbit carries it directly through a dense knot or filament of dark matter. Suddenly, the influx of fresh particles to its core skyrockets. The annihilation rate surges, and the star's engine roars to life. For a brief, brilliant period, it could flare up by orders of magnitude, emitting a powerful burst of high-energy gamma rays or X-rays before settling back into its quiet state as it moves out of the dense patch. To an astronomer's instruments, this would look exactly like a strange, short-lived cosmic explosion, a transient event with no apparent cause. It would appear, blaze mysteriously for days or weeks, and then vanish without a trace, leaving no expanding debris cloud or lingering remnant. This behavior creates a profound challenge for modern astronomy. Observatories now scan the skies nightly, cataloging thousands of these transient events: gamma-ray bursts, fast radio bursts, and mysterious X-ray flares. Most are attributed to known phenomena like colliding neutron stars or dying stars, but a few stubborn events defy easy classification. They have the wrong duration, the wrong afterglow, or occur in places where no progenitor star should exist. A transient annihilator could be the source of these oddities. Its flare would have a unique signature, a spectrum of light that perfectly matches predictions for dark matter particle annihilation, not the messy aftermath of a stellar cataclysm. Furthermore, if astronomers were lucky enough to catch the same location flaring repeatedly, say, every few hundred years as the dark star completed its orbit through the same dense dark matter cloud, it would be the ultimate clue. It would reveal a clockwork cataclysm, an explosion on a schedule dictated not by stellar evolution, but by the invisible topography of the galaxy's dark matter halo. Finding such an object would force us to connect disparate dots in our celestial maps. A gamma-ray flare recorded in the 1800s, an X-ray burst seen in the 1990s, and a new event detected tomorrow might all be the same dark star, flaring up on its long, slow journey. It teaches us that not all cosmic violence is destructive. Some brilliant flashes may simply be a dark star, breathing in and breathing out, as it sails through the unseen currents of the cosmos. A star can be more than just a source of light. It can be a cosmic sculptor. Dark star number 12, the dark matter fountain, is not a passive beacon but an active factory, forging the very elements that would seed future suns. At its heart, the relentless annihilation of dark matter particles does more than just produce energy. It creates a ferocious outward pressure, a stellar wind of unimaginable force. This is not the gentle solar wind our sun emits, but a hurricane of radiation and particles blasting from the dark star's core. As this wind screams outward, it does something extraordinary. It scoops up the star's own outer layers, the pristine hydrogen and the helium slowly cooked by the star's internal heat, and hurls them into the void. The dark star becomes a fountain, spraying its processed contents across light years of surrounding space. The surrounding primordial gas cloud, once a uniform soup of hydrogen and helium, is now peppered with these enriched jets. This enrichment is subtle but crucial. The fountain is not spraying heavy metals like iron or gold. Those come later from supernova. Instead, it is enriching the cosmos with an extra helping of helium and perhaps traces of lithium, the very first steps up the periodic table. For the next generation of normal stars beginning to coalesce in that neighborhood, this changes everything. A star born from gas sprinkled with this dark fountain's output would have a slightly different chemical fingerprint from birth. It would have a bit more helium in its core than a star formed from completely pristine gas. This tiny alteration can affect how long that star lives, how brightly it burns, and even the ultimate fate it meets. Astronomers today, when they analyze the oldest stars in our galaxy's halo, find a puzzling spread in their helium content. Some are pure, as expected from the early universe. Others are slightly enriched, a mystery usually attributed to contamination from the very first supernova. But what if some of that early helium came not from explosions but from fountains? A dark matter fountain provides a gentler, more continuous form of pollution, a steady drizzle of light elements that could have prepared the galactic neighborhood for true starlight. Finding evidence of such a fountain would require looking for ancient star clusters with a very specific signature. We would need to find a group of incredibly old stars all sharing the same slight helium enhancement, all orbiting a common center that now holds nothing but a faint, diffuse glow of X-rays or gamma rays, the faded heartbeat of the dark star that fed them. It redefines a dark star's legacy. It was not just a source of light or an anchor of gravity. It could have been a nurturing presence, a primal forge that seasoned the cosmic ingredients, subtly guiding the evolution of everything that came after. The chemistry of the oldest stars in our sky might carry the quiet signature of a fountain that stopped flowing billions of years ago. The silent fountains of the early cosmos were not the only dark stars to find companionship. In the profound quiet before the first supernova, pairs of these giants could have formed, locked in a slow dance that would one day send ripples through the fabric of space-time itself. Dark star number 13 is not a single object, but a duet, a binary gravitational wave source. This system consists of two immense dark stars, each hundreds of thousands of times the mass of our Sun, orbiting one another in a gravitational embrace that has lasted for billions of years. Their dance is a slow and stately one, but it is not eternal. With every orbit, they lose a tiny amount of energy, radiating it away as ripples in space-time, gravitational waves. This causes their orbits to shrink, drawing them ever closer in a process called in-spiral. Eventually, they will merge, but the song their collision sings would be unlike anything we have ever heard. When two black holes or neutron stars merge, it is a violent, crashing finale. They are incredibly dense objects with hard surfaces or event horizons, coming together in a final, split-second burst of gravitational waves that rings across the universe like a struck bell. A merger of two dark stars would be a completely different kind of event. These objects, while unimaginably massive, are far less dense than a black hole of similar weight. They are vast, puffy giants. As they spiral inward, their outer atmospheres would begin to touch and interact long before their cores meet. This creates a prolonged, messy, and dynamic process. Instead of a clean, sharp chirp of gravitational waves, the signal would be a long, drawn-out drone, lasting for months or even years in the sensitive frequency band of a space-based observatory. The frequency of the waves would increase much more slowly and smoothly, a rising hum rather than a sudden shriek. This is because the dark stars deform and stretch as they pull on each other, transferring energy and mass in a complex tidal dance that delays the final collision. Future observatories like the Laser Interferometer Space Antenna, or LISA, are designed to listen for these low-frequency gravitational waves. While LISA will certainly hear the mergers of supermassive black holes, it might also pick up a signal that does not fit the template. It would be a persistent, monochromatic hum that slowly crescendos over an astonishingly long time, a signature with no electromagnetic counterpart, no flash of light, no burst of gamma rays, because the merger of two dark stars would not produce the spectacular fireworks of normal matter. Detecting such an event would be the ultimate proof, a direct measurement of the invisible shaking the foundations of space itself. It would tell us that these primordial giants did not just live alone. Some found partners, and their final, silent embrace, felt across a billion light years, would finally announce their existence to a universe that has been blind to them since the beginning. The silent merger of dark stars is not the only way they could shake the universe. Their immense presence might be felt through a different kind of messenger, one that strikes our own planet from the depths of space. Among the most baffling signals we receive are ultra-high-energy cosmic rays, atomic nuclei hurtling through the void with energies millions of times greater than anything our most powerful particle accelerators can produce. Their origin is one of astrophysics' greatest mysteries, and a dark star might hold the key. Our 14th undiscovered giant is the cosmic ray accelerator, a supermassive dark star acting as a natural particle cannon. The environment around such an object is anything but placid. Its core is a continuous storm of dark matter annihilation, flooding its surroundings with intense radiation. Furthermore, as the dark star spins, it could generate a magnetic field of staggering strength, weaving a complex, invisible web around it. When stray protons or atomic nuclei from the surrounding gas get caught in this maelstrom, something extraordinary happens. They are caught in the grip of these powerful magnetic fields and whipped around over and over, gaining a tremendous boost of energy with each pass, much like a ball being swung faster and faster on an endless tether. This process can accelerate particles to mind-bending energies, reaching the peta-electronvolt scale, which is 1,000,000 billion electronvolts. In essence, this dark star becomes what astronomers call a p-vatron, a natural particle accelerator of cosmic proportions. Now, these ultra-energetic particles eventually break free from the magnetic trap. Once liberated, they travel across the cosmos in nearly straight lines, guided only by the faint magnetic fields between galaxies. Billions of years later, a tiny fraction of them slam into Earth's upper atmosphere, creating a cascade of secondary particles that our detectors can spot. The mystery has always been tracing them back. When astronomers look along the path of the most energetic cosmic rays, they often find nothing. No supernova remnant, no active galactic nucleus, no obvious violent source in that particular patch of sky. This is where a dark star fits the puzzle perfectly. A cosmic ray accelerator would be virtually invisible in optical light, yet it would be a powerhouse of particle acceleration. Its location would appear as a blank, quiet region in traditional surveys, precisely matching the eerie emptiness we see when we trace back these cosmic bullets. There is another clue. The specific mix of particles in these ultra-high energy rays, the ratio of protons to heavier nuclei like iron, could carry a fingerprint of their source. The unique environment around a dark star, with its specific radiation fields and magnetic structure, might produce a distinct blend that differs from the output of a supernova remnant or a black hole jet. Finding a correlation between a specific, seemingly empty region of space and a consistent flux of these cosmic rays with a peculiar composition would be a major breakthrough. It would point a steady finger at an unseen engine. Discovering such an accelerator would solve a century-old cosmic mystery while unveiling a new class of astronomical object. It means that the universe's most energetic particles might not come from the most violent explosions, but from the steady, relentless power of dark matter annihilation. This dark star would be a silent marksman in the cosmic dark, firing bullets of pure energy across the universe, and we on Earth are just now learning to read the return address. Gravity bends light, and sometimes that bend creates a perfect circle of cosmic mirage. When a massive object like a galaxy cluster sits directly between us and a more distant galaxy, its gravity can warp the fabric of space, curving the faraway galaxy's light around it. From our vantage point, that distant galaxy appears as a distorted ring of light encircling the foreground cluster, a phenomenon called an Einstein ring. It is a beautiful and well-understood quirk of physics, but what happens when the lens itself cannot be seen? This is dark star number 15, the lens of darkness. Imagine a supermassive dark star, a solitary colossus adrift in intergalactic space. Its mass is immense, perhaps 100 million times that of our Sun, all concentrated into a single, invisible point. By pure cosmic chance, its position aligns perfectly between our telescopes and a vibrant, spiral galaxy billions of light-years further away. The dark star's gravity goes to work, bending the distant galaxy's light around it. The result should be a perfect or nearly perfect Einstein ring, a luminous halo suspended in the black. Yet when astronomers point their instruments at the center of that ring, they find nothing. No galaxy cluster, no bright star, not even a wisp of nebulous gas. The lens is utterly dark. They would see an orphaned ring, a circle of light with a void at its heart. This creates a profound astronomical mystery. Einstein rings are prized tools for mapping dark matter, but they always have a visible anchor, a central cluster of galaxies whose stars account for at least some of the gravity causing the lensing. An orphan ring would have no such anchor. All the lensing power would come from a completely invisible source. The ring itself would appear strangely pure, its geometry dictated by a single, point-like mass rather than the messy, extended mass of a galaxy cluster. This purity is the key clue. Computer models could quickly show that no known arrangement of dark matter alone, in the diffuse halo we typically envision, could create such a sharp, symmetrical lensing effect without any visible trace. The gravitational focus would be too perfect, too concentrated. It would point inexorably to a single, massive, compact object, a dark star. Finding such an orphaned ring would be a eureka, a moment written in light. It would require systematic surveys of the deep sky, using instruments like the James Webb Space Telescope to find these delicate rings, and then performing the deepest possible observations at their centers, searching for any flicker of starlight that is not there. The confirmation would come from silence, from the absolute emptiness where a galaxy should be. This lens of darkness does more than just hide a star. It uses the star's greatest secret, its invisibility, to reveal itself. By not being seen, it creates a signature that cannot be ignored. It turns the dark star into a cosmic magnifying glass, one that lets us see a galaxy far away while completely obscuring the hand that holds the lens. In that perfect circle of borrowed light, we would finally see the outline of the dark. That gentle, persistent annihilation engine requires a very specific set of conditions to beat nuclear fusion to the punch. The formation of those first dark stars hinged on a delicate cosmic race, a contest between cooling and collapse in the infant universe. For a normal star to ignite, A cloud of gas must collapse under its own gravity, growing denser and hotter until the core reaches a temperature of about 10 million degrees, the threshold for hydrogen fusion. To form a dark star, that cloud must find a way to stay cool and puffy long enough for a different power source to take over. This is where the unique properties of the primordial gas became essential. In the aftermath of the Big Bang, the only elements were hydrogen and helium. This pristine gas lacked the heavier atoms like carbon and oxygen that, in later eras, would act as efficient radiators, allowing gas clouds to shed heat and collapse quickly. The early universe is gas-cooled primarily by emitting radiation from molecular hydrogen, a slow and inefficient process. This slow cooling created what astronomers call a cooling flow, a gradual, gentle condensation rather than a rapid, runaway collapse. It gave the dark matter time to work its magic. As the hydrogen cloud slowly gathered, its growing gravitational pull did more than attract gas. It also began to trap the dark matter particles that permeated the young cosmos. The type of dark matter particle is crucial here. The leading candidate for decades has been the weakly interacting massive particle, or WIMP. True to its name, a WIMP interacts with normal matter only through gravity and the weak nuclear force, making it incredibly difficult to detect. But within the dense heart of a collapsing cloud, WIMP could become concentrated. Their weak interactions allow them to scatter off nuclei, losing energy and settling into the cloud's core. Once there, if WIMP are their own antiparticles, they can annihilate upon contact, releasing energy. The rate of this annihilation depends on the particle's capture cross-section, a measure of how likely it is to interact and be trapped. A higher cross-section means more particles are captured, leading to a hotter, brighter dark star. An alternative candidate, the action, is much lighter and behaves more like a wave. Actions would not annihilate in the same way, but in dense enough conditions, they could stimulate the emission of radiation, potentially providing a different kind of power source. The specific particle determines the engine's blueprint. This leads to the concept of a critical mass, a tipping point for dark star formation. For a collapsing cloud to become a dark star, the energy from dark matter annihilation must equal or exceed the energy lost by the cloud through radiation. Once this balance is achieved, the annihilation pressure halts the gravitational collapse. The star stabilizes, bloated and immense, its internal temperature kept too low for fusion by the very process that powers it. Theoretical models suggest this critical mass could be as low as a few hundred solar masses for efficient WIMP annihilation, but it could balloon to millions of solar masses if the dark matter interactions are weaker. This is a staggering scale. It means the very first luminous objects in existence might not have been small, twinkling points, but colossal, diffuse globes of warm hydrogen, their size dictated by the invisible physics of particles we have yet to touch. The formation of a dark star was not a violent ignition, but a quiet settling, a giant finding equilibrium between the crush of gravity and the gentle, persistent heat from the annihilation of shadows. Finding a phantom in the void is a hunt for the faintest of whispers. Astronomers must rely on the only force this dark star exerts, gravity, and they have developed ingenious ways to listen for its subtle effects. The first strategy involves mapping the void on the grandest scale through weak gravitational lensing surveys. Instead of looking for a single, distorted galaxy, this technique analyzes the shapes of millions of faint, distant galaxies that lie far beyond the void itself. As their light travels toward us, it passes through the void's gravitational field, which includes the influence of any hidden massive object. A supermassive dark star would create a tiny, localized warp in space-time, imperceptibly bending the paths of those distant photons. This warping causes a coherent, minute distortion in the shapes of the background galaxies, stretching them in a specific pattern around the dark star's location. It is not a dramatic Einstein ring, but a statistical ripple. By using powerful telescopes to meticulously measure the orientations of hundreds of thousands of galaxy shapes in a patch of sky containing a cosmic void, astronomers can create a mass map. They are looking for a concentrated knot of gravitational influence where the map shows extra mass, but the optical image shows only empty blackness. This is the ghost's footprint in the cosmic sand. A more targeted approach searches for a wobble in the sparse stellar population that does border the void. Even in these deserts, a few ancient, lonely stars exist. Precision astrometry, the science of measuring stellar positions with extreme accuracy, could detect the proper motion wobble of these stars. If a dark star is moving through the void, its gravity will tug on any background stars that happen to lie in its path. From our vantage point, those distant stars would not appear to move in a perfectly straight line. They would exhibit a tiny, slow, curving drift as the invisible mass passes by and deflects their light, a phenomenon called astrometric microlensing. Missions like the European Space Agency's Gaia Observatory are already mapping the motions of over 1 billion stars with unparalleled precision. By combing through Gaia's data and focusing on stars that appear to be on the edge of nothing, scientists could search for these unexplained, gentle curving motions that suggest an unseen, massive companion drifting through the abyss. It would be like watching a single floating leaf in a still pond suddenly twitch, revealing the passage of a submerged giant. Yet a gravitational anomaly alone is not proof. The final, crucial step is to rule out every other possibility with deep, multi-wavelength observations. If a weak lensing survey or astrometric wobble points to a specific, empty coordinate, the world's most powerful telescopes would turn their gaze there. They would stare at that point for days, collecting every possible photon. They would look in radio waves to rule out a cold, failed star. They would examine infrared deeply to exclude a shrouded galaxy or a cloud of cold dust. They would use X-ray and gamma-ray telescopes to search for the faint, telltale glow of annihilation radiation that might leak out. The goal is to achieve a profound and definitive silence. The confirmation of a phantom comes not from what is seen, but from what is conclusively not seen after an exhaustive search. It is the process of elimination on a cosmic scale, leaving only one extraordinary explanation standing: a million solar, mass dark star, a relic of creation, drifting alone in the eternal night. Finding it would mean our maps of the cosmos are missing entire mountains, hiding in the blank spaces we once thought were empty. A galactic core pretender would not just sit quietly on its throne. It would leave a unique signature in the data, a subtle but detectable difference from a true supermassive black hole. The first clue lies in the quality of its light. A dormant black hole is a dark, quiet beast, emitting very little on its own. A dark star of similar mass, however, hums with the constant energy of dark matter annihilation. This process would generate a persistent, soft glow, likely strongest in the ultraviolet or soft X-ray part of the spectrum. It would be a gentle, steady excess of radiation emanating from the very center of the dwarf galaxy, a warmth that a sleeping black hole simply would not produce. This is not the fierce, flickering X-ray blaze of an active accretion disk, but more like the constant, low-grade heat from a banked fire. Observatories like the Chandra X-ray Observatory or the Hubble Space Telescope, by staring at the cores of suspicious dwarf galaxies, could spot this unexplained, soft luminosity right where a black hole's shadow should be. The second major difference would be the absence of relativistic jets. Supermassive black holes, even when not feasting, can sometimes power vast, narrow beams of particles shot out at nearly the speed of light. These jets are a hallmark of black hole physics, requiring an event horizon and an intense magnetic field in an accretion disk. A dark star core, lacking that extreme environment, would be incapable of producing such focused, energetic outflows. So if astronomers see a dwarf galaxy with the gravitational heft of a central monster, but completely lacking any trace of radio jets or high-energy particle beams. It raises a red flag. The core is massive, but it is not playing by a black hole's rules. Perhaps the most telling signature, however, is written in the motion of the stars that swarm around it. This is the velocity dispersion profile. Around a supermassive black hole, stars are whipped into incredibly fast, random orbits very close to the center. The graph plotting stellar speed against distance from the core shows a sharp, steep spike right at the galactic center. A dark star, while immensely massive, has a different structure. It is a physical object with size, not a dimensionless point. Its gravity field near its surface would be intense, but it would not create the same extreme, point-like gravitational well. The velocity dispersion profile around a dark star core would still be high, indicating a lot of mass, but the spike would be slightly rounded or softened. The stars would not reach those same insane velocities right at the very center, because the mass is spread out over a larger volume. Detecting this subtle difference requires exquisitely precise measurements of star motions, something next-generation telescopes are being built to achieve. It is the gravitational fingerprint of the object, and for a dark star, that fingerprint is uniquely blurred. Finding a dwarf galaxy core with a soft X-ray glow, no jets, and a softened velocity spike would be the trifecta of evidence. It would point not to a hole in space, but to a star born from the dark, a pretender king whose gentle light has been masquerading as a monster's shadow for billions of years. The data from a single, hypothetical system could turn speculation into a detailed blueprint for discovery. Let us simulate a dark binary partner, a system we will call Celestia Prime. In our model, Celestia Prime consists of a visible star, nearly identical to our own Sun, and its invisible companion, a dark star roughly 1,000 times more massive. They orbit a common center of gravity every 5 Earth years. For astronomers, the first clue would appear in the radial velocity curve, a graph plotting the visible star's motion toward and away from us. Because the Sun-like star is much less massive than its dark partner, it swings in a wide, dramatic orbit. Its radial velocity curve would show a pronounced, repeating wave, a clear sign of a massive companion. The amplitude of that wave tells us the minimum mass of the unseen object. And in this case, the number is staggering, far too large for any known type of planet or brown dwarf. The orbit itself holds another clue. A dark star's internal structure, with energy generation spread throughout its volume, could give it a slightly different gravitational profile than a normal star of the same mass. This might imprint a tiny, telltale asymmetry on the radial velocity curve, a subtle kink in the smooth wave that advanced instruments could detect over decades of observation. But gravity's story is only half the evidence. The dark star's constant annihilation glow would bathe one hemisphere of its Sun-like partner in a persistent stream of high-energy photons. This creates a thermal asymmetry. The irradiated side of the visible star becomes perpetually hotter and brighter than the dark side. As the two stars orbit, we see this star's apparent brightness and color change in a regular cycle. When its hot, irradiated face is pointed toward Earth, it appears slightly brighter and bluer. Half an orbit later, when its cooler side is visible, it dims and reddens slightly. This produces a distinct, sinusoidal pattern in the light curve, a periodic brightening and dimming that cannot be explained by eclipses, as the dark star emits no visible light to be blocked. The timing of this thermal variation would be perfectly synchronized with the radial velocity curve, confirming the source is the invisible companion's radiation. The most dramatic signal, however, might come in bursts. Our simulation adds a final layer, a dense stream of dark matter flowing through the galaxy. As the binary system orbits, the dark star might periodically plow through this stream. Each passage would cause a temporary surge in the annihilation rate at its core. For a few days or weeks, the dark star's gamma-ray output could flare by a factor of 10 or more. From Earth, we would see the Celestia Prime system light up in high-energy gamma rays, a brief, brilliant spike that then fades on the same 5-year schedule. A repeating, clockwork gamma-ray flare from a system with a massive, invisible gravitational companion and a thermally distorted visible star is a combination that is virtually impossible to explain with any conventional astrophysics. This simulated case study transforms the search from a vague hope into a concrete checklist. Astronomers would now look for a system that ticks every box: a gravitational wobble indicating a monster mass, a light curve showing asymmetric heating, and a high-energy heartbeat that pulses with the rhythm of the orbit. Finding Celestia Prime would not be a lucky accident, but the result of knowing exactly what signature to hunt for in the mountains of data from our telescopes. It makes the phantom tangible, giving it a predicted heartbeat, a thermal fingerprint, and a schedule we could mark on a calendar. A dark star's life is measured in eons, not millennia. The fate of a relic like our Dark Age survivor hinges on a single, quiet question: can its dark matter fuel last? In the sparse halo of a modern galaxy, the supply is not infinite. The star feeds by capturing dark matter particles from its surroundings, but as it consumes them, the local density slowly drops. Over billions of years, this gradual starvation would force a profound change. The steady outward pressure from annihilation, which once held gravity at bay, begins to wane. Gravity, patient and relentless, starts to win. The star's immense bulk begins a slow, inexorable contraction. This is not a catastrophic collapse, but a glacial sinking as the star squeezes itself over hundreds of millions of years. As it shrinks, two paths diverge. In the first, the compression heats the core. Remember, this star is made of pure hydrogen and helium, the perfect fuel for nuclear fusion. If the contraction raises the core temperature to that critical threshold of around 10 million degrees, something extraordinary happens. The dark star's original engine sputters and dies, but a new one ignites. Hydrogen begins fusing into helium, and the relic transforms. It becomes a normal, fusion-powered star, albeit one of incredible age and bizarre origin. Its light would change, shifting from the soft glow of annihilation to the fiercer blaze of nuclear fire. This late-blooming sun would be a cosmic anomaly, a star that spent its first 10 billion years in a different state entirely. The second path is darker. If the dark matter fuel runs out before the core gets hot enough for fusion, or if the star is simply too massive, the contraction does not stop. With no internal pressure left to resist, gravity runs unchecked. The star collapses directly into a black hole. This would be a silent, invisible death. There is no supernova, no brilliant explosion to mark its passing. One moment, a faint, warm object exists. The next, a dark gravitational pit sits where it once floated. This direct collapse could explain the origin of some intermediate mass black holes we find today. Mysterious objects that seem too heavy for a stellar collapse, but too light for the supermassive monsters at galactic centers. They would be the ghostly graves of the first dark stars. So, what are the odds of finding a true relic still burning today? They are slim, but not zero. For a dark star to survive for over 13 billion years, it needed to find a perfect balance. It must reside in a region with just enough dark matter to provide a trickle of fuel, but not so much that it overfeeds and burns out quickly. The calm halo of a large galaxy like the Milky Way offers this possibility. The relic would be a faded ember, its glow so faint it blends into the sea of ancient normal stars. Spotting it would require identifying an object with two impossible traits: a chemical composition of pure hydrogen and helium, and an unexplained excess of soft radiation that defies fusion models. It is a search for a whisper in a cosmic chorus. Yet if we did find one, it would be more than a fossil. It would be a time capsule with its clock still ticking, allowing us to watch in real time the final act of a story that began before light itself was common. We would witness the last breaths of a different kind of star, a living memory of the universe's first and most mysterious dawn. Our rogue wanderers may be leaving a trail, not of light, but of motion imprinted on the universe itself. For over a decade, astronomers have been puzzled by a mysterious signal known as the dark flow. It is not a river of dark matter, but a strange, coherent drift. Observations of hundreds of distant galaxy clusters show they are all streaming in the same direction at astonishing speeds, millions of miles per hour, a motion that cannot be explained by the known distribution of matter in our observable universe. It is as if something immense, far beyond the cosmic horizon, is exerting a gravitational pull on everything we can see. The leading theories involve exotic ideas like the gravitational tug of another universe or a pre-Big Bang structure. But there is another, quieter possibility. What if the pull comes from within our own cosmos, from a population of objects we have simply never seen? This is where our legion of rogue dark stars re-enters the story. Recall that these are castaways, ejected from their home galaxies during violent mergers, now drifting in the intergalactic void. While a single rogue is insignificant, consider a vast population of them. If the early universe produced countless dark stars, and if galactic mergers were common, then the spaces between galaxy clusters could be sprinkled with millions of these invisible giants. They would form a diffuse but massive component of the cosmic web, an unseen skeleton woven through the voids. Their collective gravity, while subtle, could exert a persistent, large-scale pull on the galaxy clusters we observe. This would not be a sharp tug from one direction, but a gentle, statistical current, a drift caused by the uneven distribution of this hidden mass. The challenge is proving it. We cannot see the dark stars, and their individual effects are minuscule. The evidence would have to come from their cumulative impact on the oldest light in the universe, the cosmic microwave background. This afterglow of the Big Bang is a nearly perfect snapshot of the infant cosmos. But as this ancient light travels for over 13 billion years to reach us, it passes through everything, including the gravitational fields of all the matter in its path. When light skims past a massive object, its energy gets a tiny boost, a phenomenon called the integrated Sachs-Wolf effect. This effect leaves a specific, cold imprint on the microwave background map. Now, imagine that light passing through a region populated by rogue dark stars. Their combined gravity would subtly shift the energy of the photons, creating a pattern of very faint cold spots in the microwave sky that align with the direction of the dark flow. It would be an incredibly subtle signal, buried deep in the noise. Detecting it would require exquisitely precise future maps of the cosmic microwave background, from next-generation space observatories designed to measure its polarization and temperature variations with unprecedented fidelity. Scientists would then cross-reference these ultra-detailed maps with the observed motion of galaxy clusters, searching for a correlation between the direction of the flow and specific, unexplained distortions in the ancient light. Finding that link would be a revelation. It would suggest that the dark flow is not a pull from something outside our universe, but a push from within, from a hidden ocean of dark matter giants we have only just begun to theorize. These rogue wanderers, once thought to be lonely ghosts, could instead be a dominant population, shaping the large-scale currents of the cosmos with their silent, collective weight. They are not just drifting. They may be steering the flow of everything we see. A hidden heart beats with a warmth the darkness cannot completely smother. Within the deepest folds of a dark nebula, the dark star's engine is not just a source of light, but a source of heat. The annihilation process at its core floods its surroundings with radiation, and while visible light is swallowed by the nebula's thick dust, longer wavelengths tell a different story. Tiny dust grains, each smaller than a mote of smoke, absorb this energy. They do not glow in colors our eyes can see, but they do grow warm. This gentle heating causes them to re-radiate the energy in the infrared and submillimeter parts of the spectrum, creating a faint, telltale warmth against the nebula's profound cold. It is the thermal fingerprint of a hidden sun. To telescopes that see in heat rather than light, a dark nebula with a dark star at its center would not look uniformly black. Instruments like the James Webb Space Telescope, designed to peer through cosmic dust, would see a mysterious point of infrared warmth buried in the cloud's coldest, densest region. The glow would be diffuse and soft, not the sharp pinpoint of a normal star, because the heat is coming from a vast area of dust warmed by the star's radiation. Even more telling would be observations from arrays like the Atacama Large Millimeter Array, or ALMA, which listens to the universe in submillimeter waves. These wavelengths are perfect for studying the coldest objects in space. ALMA could map the molecular gas and dust in the nebula in exquisite detail, revealing not just a warm spot, but a specific structure. The heat from the dark star would create a gentle outward pressure, potentially carving a small cavity or bubble within the cloud. ALMA might see a spherical region where the gas is slightly warmer and less dense, a quiet hollow sculpted by an invisible force. Furthermore, the specific molecules in that warmed gas could hold clues. The unusual radiation from the dark star might excite certain molecules, causing them to emit light at very specific submillimeter frequencies that would appear as anomalous bright lines in ALMA data. It would be a chemical signature of an exotic energy source. Finding a dark nebula with a warm heart, a carved cavity, and strange molecular emissions would be like finding a sealed room with a warm fireplace, an empty chair pulled close, and the distinct scent of a rare wood in the air. You would know someone was there even if you never saw them. This transforms our search from looking for an absence of light to looking for a specific kind of presence, a subtle warmth in the coldest places. The dark nebula is no longer just a hiding place, it is a canvas, and the dark star paints its portrait in the invisible light of heat. The true unmasking of a quasar mimic lies in the language of its light. Every quasar sings a specific song written in its spectrum, the detailed breakdown of its light into individual colors or wavelengths. A true quasar's brilliance comes from a superheated accretion disk, a whirlpool of gas spiraling into a supermassive black hole at nearly the speed of light. This frantic, violent environment leaves a very clear signature. It produces intense, broad emission lines. These are bright spikes in the spectrum at wavelengths corresponding to elements like hydrogen, helium, and carbon, but they are not sharp. They are smeared out into wide, fuzzy humps. Why? Because the gas in that disk is moving at tremendous, chaotic speeds thousands of kilometers per second, in all directions. The Doppler effect from this extreme motion stretches and compresses the light, blurring those sharp spectral lines into broad bands. It is the fingerprint of utter chaos, of matter on the brink of oblivion. Now, listen for the song of a dark star quasar mimic. Its light does not come from a frenzied disk of doomed gas. It comes from the steady, internal annihilation of dark matter particles at its core. This process likely produces a very different spectrum. Instead of sharp, broad emission lines from fast-moving gas, the light from annihilation might be a smooth, featureless continuum, a clean rainbow of energy with no distinct spikes. It would be the hum of a pure energy source, unmarked by the fingerprints of normal matter being torn apart. Alternatively, if the specific dark matter particles decay or annihilate in a certain way, they could produce their own, entirely unique emission lines at very specific, high-energy wavelengths lines that do not correspond to any known element on the periodic table. These would be the spectral signatures of the particles themselves, a direct message from the dark sector. This gives astronomers a clear observational checklist. When they find a brilliant, point-like object that looks like a distant quasar, they point their most powerful spectrographs at it. First, they search for those broad emission lines. If they are completely absent, that is a major red flag. Second, they examine the continuum. Is it suspiciously smooth, or does it show unexplained spikes at strange energies? Third, they look for variability. True quasars flicker and flare as their accretion rate changes. The glow from a dark star's annihilation engine could be remarkably steady, a clockwork beacon in contrast to a flickering torch. A candidate that passes all these checks, no broad lines, a smooth or oddly featured continuum, and unwavering brightness, would cease to be a quasar in the logs. It would become something far stranger. A billion solar, mass dark star, its brilliant light a facade powered by the silent annihilation of the universe's most mysterious substance. We may have already catalogued these mimics, filing them away as ordinary quasars, simply because we never knew to listen for the quiet, featureless song hidden within their dazzling glare. The center of our galaxy holds a strange and persistent glow. For over a decade, the Fermi Gamma Ray Space Telescope has mapped the sky in the most energetic light, revealing a mysterious excess of gamma rays emanating from the Milky Way's core. This signal, known as the Galactic Center GV excess, is a diffuse, spherical halo of high-energy photons with no obvious source. Its very existence has ignited a fierce debate. One compelling theory points to dark matter. If dark matter particles are their own antiparticles, they would annihilate when they meet, and a dense region like the galactic center is the perfect place for that to happen. The resulting energy could produce the exact pattern of gamma rays Fermi sees. The alternative explanation is astrophysical. It suggests the glow comes from a vast, unseen population of millisecond pulsars, the rapidly spinning corpses of dead stars, whose collective radiation could mimic a smooth signal. The data remains ambiguous, a cosmic Rorschach test where experts see different pictures. This is where our Halo Sentinel offers a fascinating third possibility. The debate assumes the signal is either entirely from a smooth cloud of annihilating particles or entirely from point sources like pulsars. But what if it is a mix of both? A handful of supermassive dark stars, like our galactic halo sentinels, could be orbiting the galactic center at various distances. Each one would be a powerful, steady point source of annihilation gamma rays. From our distant vantage point, the combined glow of just a few dozen of these massive, invisible objects, scattered throughout the inner halo, could blend together into a diffuse, spherical excess that perfectly matches the Fermi data. They would be bright, singular annihilators, not a smooth cloud. This hybrid model elegantly addresses the weaknesses of the other theories. For the pure dark matter interpretation, a major challenge is that the signal's shape and brightness suggest dark matter interactions that are stronger than many particle physics models allow. A few concentrated sources, however, would require far less total dark matter interaction to produce the same observed glow. For the pulsar interpretation, the problem is that we have not found enough of these pulsars with radio telescopes to account for the signal. Dark stars would be radio quiet, explaining their absence in those surveys. The key to testing this idea lies in the fine details of the gamma ray map. If the excess is truly from millions of faint pulsars, its texture should be subtly grainy. If it is from a smooth dark matter cloud, it should be perfectly uniform. But if it comes from a moderate number of bright, point-like dark stars, advanced statistical analysis might reveal a hint of lumpiness, a suggestion of brighter knots within the smooth glow. Future gamma-ray telescopes with higher resolution could hunt for these statistical clumps. Finding them would not just solve the Fermi puzzle. It would point a direct finger at the locations of individual dark stars, transforming a mysterious glow into a star map of the invisible. The Sentinel's silent song, it turns out, might be a chorus we have been hearing all along, woven into the brightest and most puzzling signal from the heart of our own galaxy. The supercomputers that model our universe are beginning to include the strange physics of dark stars, and the results are reshaping our cosmic origin story. These are not simple animations, but mathematical universes, born from the fundamental laws of physics and evolved over billions of simulated years. When scientists program in the possibility of dark matter annihilation as an energy source, something remarkable happens in the virtual dawn. The first luminous objects to form are not small, twinkling points. They are vast, diffuse spheres of glowing gas, the dark stars, and they often appear not alone but in groups. These simulated dark star clusters form at the intersections of dark matter filaments in the early cosmic web, where the density of both gas and dark matter is exceptionally high. A single simulation box can show dozens of these dark clusters igniting, each one a gravitational anchor holding millions of solar masses of invisible and visible matter in a loose, warm embrace. This changes the entire timeline of early structure formation. These clusters light up millions of years before the first supernova ever explode, providing gentle, persistent radiation that begins to slowly cook and ionize the hydrogen fog of the young cosmos. They act as the universe's first streetlights, illuminating the neighborhoods where true galaxies will later grow. But the most compelling evidence from these simulations lies in what they leave behind, a signature we might be seeing in the sky right now. The ancient globular clusters orbiting our Milky Way are cosmic fossils, balls of hundreds of thousands of stars that formed in one intense burst over 13 billion years ago. Many are incredibly metal-poor, meaning they contain almost none of the heavy elements forged in stellar explosions. This purity is a puzzle. If these clusters formed from gas enriched by the very first supernova, we would expect to find at least a trace amount of those heavier elements mixed in. Some clusters, however, are so pristine it suggests they formed from gas that was never touched by a supernova at all. This is where the dark star cluster progenitor offers a perfect solution. In the simulations, a cluster of dark stars lives for millions of years, glowing and enriching its surroundings only with the helium and lithium from its gentle winds. When these dark stars finally die, either fading or collapsing quietly into black holes, they leave behind a cloud of pristine, slightly helium-rich gas. It is a clean nursery, untouched by the violent pollution of exploding stars. Only then, in this prepared environment, do the first normal stars ignite, forming a tight, gravitationally bound cluster that we see today as an ancient globular cluster. The simulation predicts that the stars in such a cluster would have two key traits: a complete absence of heavy metals and a slight, uniform enhancement of helium. This matches the bizarre chemistry of some of the oldest clusters we have found. Finding a real globular cluster with this exact chemical fingerprint would be like finding a fossil with the imprint of a creature we have only ever simulated. Astronomers are now using the world's most powerful telescopes to take detailed spectra of individual stars within the oldest known clusters, searching for that telltale helium signature amid the profound metal poverty. It is a painstaking process, measuring the faint light from ancient suns to decode the recipe of the cloud that formed them billions of years ago. If the match is found, it would mean these majestic, glittering swarms of stars are not the first generation. They are the second. Their brilliance is built upon the invisible, dark foundations of the true first generation, a family of dark stars that lived, glowed softly and died quietly, leaving behind a purified cradle for the stars we can finally see. 25 possibilities, each a doorway into a cosmos we are only beginning to perceive. From the solitary phantom in the void to the brilliant quasar mimic, from the nurturing fountain to the binary pair singing gravitational waves, this is not a list of objects. It is a map of a hidden frontier. Each dark star concept represents a different conversation between the dark universe and the visible one, a unique signature written in gravity, radiation, and subtle, telltale heat. They challenge our most fundamental assumptions, suggesting that the first light was soft, the brightest beacons might be facades, and the empty spaces are full of silent giants. This is the thrilling edge of modern astrophysics, where wild theory meets painstaking observation, and the next dataset could rewrite a chapter in the story of everything. The hunt is on, fueled by simulations, guided by anomalies, and carried out by telescopes that see in every kind of light. The discovery of even one of these dark stars would send ripples through physics and cosmology, forcing us to redraw the family tree of celestial objects. It reminds us that the universe is far stranger, more creative, and more mysterious than we have dared to suppose. So keep looking up and keep wondering. The next big revelation might not be a flash in the night sky, but a whisper in the data, a pattern in the silence, a single observation that finally illuminates the dark. Which of these 25 undiscovered giants captured your imagination the most? Let us know in the comments and stay curious. The dark cosmos still has countless secrets